Good evening, everyone. I'm just waiting for people to join us. So a few more people just coming in and then we'll make a start in just a minute. It's lovely to have you all here. We'll give it 30 seconds longer and then we'll get started. Okay, we'll get started. Good evening, everyone, and welcome to the Ultimate Exam Technique Programme for Science. This is, of course, the physics session. It's the first physics session of the programme. Some of you will have had the biology and chemistry. Some of you might be joining the programme for the first time. My name's Sarah, and I'm going to be taking you through our session this evening. Our session today covers the energy part of the physics specification. I've followed the AQA specification. Don't worry if you're doing OCR or Edexcel. The content is very, very similar. The specifications, are very subtly different. The main differences are the way the exams are structured, as opposed to the actual content being different. And this is suitable for those of you doing the foundation paper, higher paper, combined or separate science. I'm sure you've seen this before. Your teachers at school have probably shown you it. If you've done chemistry and biology, I know Claire showed you it on Monday. I'm not sure if Becky showed you it yesterday as well. So we've got a little breakdown there of the paper. So what we're looking at today is energy. So it's in paper one, and it's in paper one of both the separate and the combined science. And this is the specification. So this is the huge document that teachers use to plan your lessons, because this is provided by the exam board, and the exam board can examine you on any of this. So just at a very quick overview, you will see that we need to know about energy stores, changes in energy. We need to be able to calculate kinetic energy and elastic energy, as well as gravitational potential energy. We need also to calculate specific heat capacity. So there's a link here with another part of the physics specification. It comes on a little later in paper one, but this part also cross-links with your chemistry as well. You'll see there's a required practical activity here, and this is being able to determine the specific heat capacity of materials. So hopefully you've done that in school. At the very least, you should have seen a video of the required practical. And that required practical is for both combined science and separate science. We also need to know something called the conservation and dissipation of energy. So conservation of energy means energy isn't lost. It's not created and it's not destroyed. It's just transferred from one form to another. We also need to be able to calculate efficiency. And required practical activity too, you'll see this says physics only. So this is for those just doing the separate course. And this required practical is all about thermal insulators and how well different materials act as thermal insulators. So again, hopefully you've done that in school, or at the very least you've seen a video of it being done. The only higher tier content for this part of the specification is describing ways that efficiency can be increased. So the vast majority, the 99% of the energy specification is for all candidates, whether you are doing higher tier, foundation tier, combined or separate. All of today's exam questions that we're going to look at, they are all applicable to both combined science and separate science. Some are foundation, Some are higher and some are cross paper. So the foundation and the higher papers overlap. The top end of the foundation paper you will find on the lower end of the higher. So there is some of those crossover questions here as well. And finally, this unit is huge. We also need to know about energy resources. So renewable energy, non-renewable energy. The specifications are available for you as students as well. You can find them on the AQA website if you want to use them. Some students do act as a checklist, others just decide not to because they can be quite overwhelming. They are huge documents, but this is no secret. Okay, teachers use it to plan, but it is also available to you as well. Okay, right, let's get started. Before I do begin to get into this question, I would like to say that if you have any questions as I'm working through this, please type them into the chat. Every question has a number on it and it's in the top right-hand corner. So this one's question 1, as you can see. So if you had a question about this question, you would type in the chat question 1 and then your question, so that when I look back through the chat at the end, if there are any questions, I know which question you were on about when you asked me. No question. So let's get started. You'll have to forgive me. I had a camera malfunction at the beginning, which is why I was a couple of minutes late getting on. My integrated camera on my laptop is just kaput. It is not working anymore. So I've had to use my temporary camera, which isn't ideal because it's overlapping part of my screen. So every now and again, if I kind of dip to the side, it's just because I'm looking around the camera to see the question. I will have a new camera ahead of next week. So anyway, I'll stop talking about my camera issues and get started. So this, as you can see, I think, let's see around there, is, yeah, this is from a foundation paper. And we have a cyclist cycling along the road, and we are asked to complete the sentences. Choose answers from the box. When it says choose answers from the box, please only use answers that are in the box. I know it sounds self-explanatory and really straightforward, but the number of times that we see as teachers and as examiners, people putting words on these lines that aren't in the box is unreal. You would be surprised. So when the cyclist accelerates, the blank energy store of the cyclist's body decreases. Okay, well, let's have a look at the words. We've got chemical, elastic potential, gravitational potential, and kinetic. Kinetic energy is movement energy. So anything which is moving has energy in the kinetic store. Anything which is high up has energy in its gravitational potential store, and anything which is stretched or compressed has energy in its elastic store. Chemical energy is found in our muscles. It's also found in our food, and people often don't make the link there, chemical energy to our muscles. But of course, as the cyclist is accelerating, he is using energy, and that energy is coming from the chemical energy store in his muscles. So the chemical energy store is going to decrease over time as he uses that energy to cycle. But because energy is conserved, that chemical energy isn't just destroyed, it gets turned into a type of energy in the bike, and the bike begins to move. In this case, it begins to accelerate, so it speeds up. So therefore, the kinetic energy of the cyclist increases. So we have an interchange between two stores here. The chemical energy store of the muscles of the cyclist reduces. At the same time, the kinetic energy of the cyclist increases. And we now have a calculation to do. The mass of the cyclist is 80 kilograms. I'm going to underline that because that's a number that I'm going to need to use. The speed of the cyclist is 12 meters per second. I'm going to underline that as well. Calculate the kinetic energy of the cyclist. And we have the equation. Kinetic energy equals 0.5 times mass times speed squared. So 0.5 is a constant, okay? That number won't change. It's always 0.5 in the kinetic energy equation. That's the first thing to note about this equation. The second thing is don't forget to square speed. People often forget to do that. If you're not sure how to use the squared function on your calculator, then just times the number by itself. That's all squared means. And it's always good practice to lay out your calculations, any calculation-based answer, as I'm about to show you now. So I'm going to write kinetic energy. So energy, and then a little k, that means kinetic energy, equals 0.5 times mass times speed squared. So I'm just laying out what I'm going to use. Now I fill in the numbers. So 0.5 is a constant, mass was 80 kilograms, and speed was 12. Remember, that needs to be squared. I'm then going to write it out again, but this time I'm going to square the 12. And now I have that calculation just as I need it. Everything is in the correct units, and I've squared speed. So I can go ahead now and add that into my calculator, and it gives me an answer of 5,760. There's no units required, it's already there. But we measure energy in joules, which is why we have the J. And this is 2 marks. So it's 2 marks because I suppose we're already given the calculation, so it's no more than that. But yeah, we do need to make sure we do this squaring in the kinetic energy equation. If you are sitting your exams this summer, you will be given the equation sheet for your physics exam. So that's a bonus. That is good news. Okay, so we've got the answers there. I don't think there's anything to note from this mark scheme. It's pretty straightforward. All right, so I'm just going to have to dip around my camera here again. So part of the same question, when the cyclist uses the brakes, of course, the cyclist and the bicycle slow down. And this causes the temperature of the brake pads to increase, and it increases by 50 degrees C. I'm going to circle that just because I think it might be important later on. The mass of the brake pads is 0.04 kilograms. I'm going to underline that. And the specific heat capacity of the material of the brake pads is 480 joules per kilogram per degree Celsius. Specific heat capacity tells us the quantity of energy that we need in joules to raise 1 kilogram of a substance by 1 degree Celsius. So in this case, we need 480 joules to raise 1 kilogram of the brake pad material by 1 degree Celsius. And the units give us some clue as to what is going on with specific heat capacity. Joules is energy, kilograms is mass, and degree Celsius is temperature. And we have an equation here to use, so that's great. Let's calculate the change in thermal energy. Well, change in thermal energy equals mass times specific heat times temperature change. So let's fill in those numbers. Mass, we were told, is 0.04 kilograms. The specific heat capacity is 480 joules per kilogram degree Celsius. And finally, the temperature change, well, the brake pads increased by 50 degrees Celsius. Once we write that out, there's nothing to change, there's no units to convert, there is nothing to go ahead and square, so we can therefore put that into our calculator, and it gives us an answer of 960 joules. So that's the change in thermal energy. And that's how vehicles, bicycles, how they slow down. In order to slow down, they need to lose kinetic energy. And so what they do is they transfer the kinetic energy to the thermal energy of the brakes, and therefore reduce the kinetic energy, so the bike, the car, whatever vehicle it is, slows down. We're then asked, how does the internal energy of the particles in the brake pads, how is that affected by an increase in temperature? Well, internal energy is a measure of 2 things. Number 1, it's a measure of the kinetic energy of the particles. So kinetic energy is the movement energy. The more movement energy the particles have, the more kinetic energy they have. And it's also a measure of the potential energy that coming from the distance between the individual particles. Now, the internal energy of the particles in the brake pads is going to be affected by this increase in temperature. Increase in temperature means increase in kinetic energy, because if the particles have more temperature, they have more energy. And so therefore, we're going to see an increase in the internal energy as the kinetic energy store of the particles is increased due to the increase in temperature. Again, I'm going to have to dip around my camera to see this. What is that? Okay, so we have different energy resources, and they were used to generate electricity. Just, was it one day I can see there in June 2018. So we've got a pie chart. Now we've got the pie chart with different shadings to show us the different energy resources. We are then told that the UK government plans to stop using coal-fired power stations from the year 2025. Explain one environmental problem caused when electricity is generated by burning coal. Okay, so anything to do with burning fossil fuels, we should make links to carbon dioxide emissions. So burning fossil fuels should always make you think, number one, carbon dioxide. Burning fossil fuels releases carbon dioxide. What's the problem associated with carbon dioxide? Well, it leads to enhanced global warming. And that would be sufficient for your 2 marks. Carbon dioxide is released, which leads to enhanced global warming. But it doesn't stop there. We can also mention, when we have fossil fuels burning, we can also mention sulfur dioxide as well. And sulfur dioxide is linked with acid rain. So the sulfur dioxide dissolves in the water in the atmosphere, leading to acid rain, which damages aquatic communities. It leads to trees being damaged and so on. But what I'm trying to show you here is that there's links to be made. Burning of coal, burning of fossil fuels should always trigger you to think of carbon dioxide. That's problematic because it leads to enhanced global warming. Sulfur dioxide, that's problematic because it leads to acid rain, which damages aquatic habitats and damages trees. We needed to give 2 renewable energy resources that could make up the other category. So renewable energy resources are those which are described as infinite. So we can continue to use them time and time again to meet our energy needs. Coal, oil, and gas, these are non-renewables. Nuclear actually is non-renewable as well. People often think that nuclear is renewable for some reason. Coal, gas, also oil, and nuclear, they are all described as being finite. So one day they will run out. But here we need to be concerned with the other energy sources. So what could we have there? We could have wind. We can use the wind to generate power. We could have geothermal, so using hot rocks underground to heat water, to get steam, to turn a turbine, to generate electricity. We could use biofuels, so that's the burning of biological material, so chop down trees, for example. We could use wave power. We only needed to give 2 though. So when we are asked what could make up the other category, please don't list things that are already there in the key, because you're not going to get a mark for that. You're just writing down whatever is up there down here. You're not going to be awarded any credit for that. And we are asked to determine the percentage of electricity generated in nuclear power stations that day. So you'll notice nuclear power currently doesn't have a number in its section of the pie chart. The pie chart, of course, adds up to 100%. So we need to work out what we already have here. So we need to add 23 and 24 and 3 and oops, that should be a plus, and 28, and that equals 78. Our pie chart should equal 100, so what is left over is 22. And so therefore, nuclear power is responsible for 22% of the electricity generated on this particular day. Okay, just looking at myself down there in the bottom corner, and I'm not happy with my camera at all. Anyone who's joined us since I've mentioned my camera, it malfunctioned. My laptop camera, I think, has had its day and it's broken. Thankfully, though, I had a spare, but I'm not happy. I'm not happy with the positioning of it. But I couldn't waste time setting it up. I needed to get online for you guys. All right, so again, I'm going to have to dip around this here because I can't see the thing. So it shows us how the demand for electricity varied during the course of a day. So whenever you're presented with a graph, always take time just to familiarise yourself with the axes. What have we got going on along the bottom? Well, this is the time of day. So that's going to be midnight, 6 a.m, midday, 6 p.m, midnight. What have we got going up the side? Demand for electricity. So the higher the number, the higher the demand. What was the difference between the maximum demand and the minimum demand for this day? So maximum means biggest. We need to read off here because that's where the demand was highest. And the lowest, well, that's down here at the bottom. And we need to work out the difference between them. So what have we got? Our highest was 37,500. The lowest was 25,000. And the difference between them is 12,500. Always check that you are given a unit. If you're not given a unit, you will need to include one, but no worries here because we have a unit provided. Now, figure 7 shows us that the demand for electricity increased. So that means more electricity was needed between 6 a.m. and 9 a.m. Solar power, so using solar panels, could have met the demand if there were enough solar panels installed in the UK. Explain why. Right, well, let's just check out the time. 6 a.m. till 9 a.m. What's going on there? Well, the sun is rising. And why is that significant? Well, it's significant because solar panels, of course, they generate electricity using the sun. And between 6 a.m. and 9 a.m., the sun is rising. Oops, sun is rising. Oh, the sun's shining. I suppose it depends on the time of year. At the moment, I don't know what time sunrise is. Might be around about 6 o'clock. I don't know. But obviously on a summer's day, then yeah, it's going to be rising around about that time. So the sun's rising, or in the summer it's already shining. So that's great. That's perfect timing to use the solar panels. Solar panels use the sun to generate electricity. Between 6 a.m. and 9 a.m., the sun's rising and it's shining. So there's lots of solar energy that the panels can use to generate electricity. Okay, so I'm just looking here and I just want to highlight something. So that question about the solar panels, you will notice it was worth 2 marks. So we should always look at the number of marks available to guide a written answer like this. So it wouldn't be sufficient to just say solar panels. Oops, that should be E. Solar panels use the sun. Like, number 1, that isn't correct anyway. We need to be referring to the sun's light energy. But also, that's never going to get you 2 marks. And we see this again time and time over. For a 2 mark, 3 mark, 4 mark question, students will write 1 sentence. And that is never going to get you 4 marks. But people do still think, well, if it's correct, it's surely worth 4 marks. If a question's worth 4 marks, you need to make 4 points. It's not 4 marks for writing one correct sentence. It's 4 marks because it needs to be an extended response and we need to be making at least 4 valid points. So we can see here, we need to make sure we're making 2 valid points. And there's a choice, you know, and sometimes we see this with written answers. Well, frequently we see it. There is an option. There's various things you could have said to be awarded that second mark. So the power output would increase throughout the morning. That's correct. As the sun rises and begins shining. So the power output would increase. And between 6 and 9, the sun is rising or shining. So there was 3 things we could have said there. We only need to say one of them, but 3 things to be awarded that second mark. If you have joined us since the beginning and you didn't hear me say, you are welcome to ask any questions by typing them in the chat. If you do so, please reference the question number that your question refers to, and the question number is always in the top right-hand corner of the screen. Just before I move on, I'm going to see if I can move my camera a little, because I'm aware that you're not really getting to see my face. Not that that's important, but I think that's no good. Is that any better? It's a little bit better. I'm not going to spend too much time on it, but I think it's important you can see all of my face. Okay. So I'm going to have to peep behind my camera again. So this is from, I've said higher foundation. So this is one of these questions where it's at the top end of the foundation paper and it appears on the lower end of the higher. So it's one of those crossover questions. And we're given 2 pieces of information. Just grabbing my pen, I'm going to have a look behind here again. So we've got figure 11 shows us how temperature varies for water in a tank heated with an immersion heater. Figure 12 shows us how temperature varies when we have water being heated with a solar panel. Okay, so again, spend time just familiarizing yourself with what the charts are showing you. So we've got time along the x-axis. We've got temperature of water up the side. Okay, so beginning to see what's going on here. The immersion heater seemed to have a sharp dip in temperature of water, but a rapid increase. Okay, and whereas the solar panel, we have a steady increase in temperature slowly throughout the day. All right, so I'm already familiar with what's going on in the figures. I'll now have a look at what the questions are asking me. So, 8.3, give one advantage and one disadvantage of heating the water using solar panels rather than the immersion heater. Use only information from figure 11 and figure 12. In other words, don't put like your own ideas in. I know you might have them, advantages and disadvantages of solar panels. You might have lots of ideas. Only use the information in the graphs. So we don't want to see things like solar panels are expensive. Solar panels don't look very nice on the roofs of houses. The maintenance problems can be expensive. All of those things might be valid, but not in this question because we are asked to refer to only figure 11 and figure 12. So our advantage and disadvantage must come from the figures. Well, the advantage of the solar panels, we can see that water is heated continuously throughout the day. So we don't have these like reduction in temperature like we do with the immersion heater. So the water temperature keeps dipping throughout the day. We don't have that with the solar panel. So the solar panel is a good thing in that the water is heated continuously throughout the day. Now, disadvantage of solar panels, remember it needs to come from the figures. Well, the disadvantage is that imagine you wanted a shower at, I'm trying to get my rubber. Imagine you wanted a shower at 9 o'clock in the morning, 9 a.m. You're going to have a very cold shower. Even if you wanted a shower at 10 o'clock in the morning, still pretty cold. Before you get a comfortable temperature of water, we're later on in the day. So that's a disadvantage. The water takes a long time to heat. That's one. I'm going to make some more points. You wouldn't need to. It's only worth 2 marks. So it's 1 mark for the advantage and 1 mark for the disadvantage. But there are a couple of things you can mention here. The water might not be hot enough. So you having a shower at 9 a.m., you're going to have a very cold shower. Whereas we don't have that problem with the immersion heater. Might not be. You know, I do that when I'm talking and writing at the same time. The water might not be hot enough. With the immersion heater, you can see the water temperature increases rapidly. So that's really good, right? I want a shower, I'll put the immersion on. Half an hour later, well, not even that, 20 minutes later, temperature's hot enough. Great. Not the case with the solar panels, though. I've got to wait. It's all right if you want your shower at like 3 o'clock in the afternoon, but not if you want one before school, before work, whatever. It's going to be too cold. During one morning, a total of 4,070,000 joules of energy is transferred from the electric immersion heater. 4,030,000, okay, those numbers are different. Just be careful there. So when we're in an exam situation and we're anxious and our heart is pumping and we've got lots of adrenaline flowing, it can be very easy to make silly, like miss things, you know, make silly errors, and confusing those numbers for being the same thing could be one of them, because I nearly missed it then. And I've looked at this quite a few times in preparation for this evening. Okay, so 4,030,000 joules of energy transferred to the water. Calculate the proportion of the total energy transferred to the water. Okay, well, a total of 4,070,000 joules, remember it's energy, energy is measured in joules, that's transferred from the immersion heater. And this many, 4,030,000 joules are transferred to the water. Now, we need to work out the total energy transferred here. And we've got 2 marks. Right. I'm just looking, I was expecting, there's no time on there. Where's time? I'm just looking because I was expecting another value on there, and it's not there. Where is it? Let me check where I put that. Is it on the next slide? No, it's not. I was expecting another number. I think I've jumped ahead. I think that must be on the next bit. So 2 marks. Okay, so quite straightforward for this then. And write them out again now. 4,070,000 joules transferred from the immersion heater, and 4,030,000 joules are transferred to the water. So the energy transferred to the water. Okay. This is where I need to grab my calculator. I remember when I was your age, like, you know, you're 10, you're 11, my teachers would always say to me, you need to learn to do sums in your head, because we're never going to be at a stage where we're all carrying calculators around in our pockets. And now we certainly are. And we get a proportion of total energy of 0.99. Okay. Now we've got a question here. This is the same question, but different part. We are asked, I'm just dipping under my camera, write down the equation. Now remember, you guys are going to, if you're sitting your exams this summer, So if you're year 11 currently, you will have an equation sheet. So you're probably not going to get 1 mark questions where you're asked to write out a calculation, because it's going to be on the sheet. And all you're going to need to do is copy it over from one place to another. So I don't think these ones will appear. But anyway, energy transferred is equal to power times time. So I'll put that there so we can refer to it now. So the power output of an immersion heater is 5,000 watts. So power, that's the unit there, is watts. Energy, we already know, is in joules. Time in physics is measured in seconds. Calculate the time taken for the immersion heater to transfer the 4,070,000 joules of energy that was referred to in the last part of the question. Now there's 4 marks here. Now, whenever you see 4 marks for a calculation question, you can it's probably the case that you need to do some rearranging of an equation. So it's not as straightforward as just, putting in the numbers in the order of the equation that's given on the formula sheet. It's probably going to be some rearranging. You're probably going to need to give a unit. Yeah, we can see there, we do need to give a unit as well. So I'm going to, again, structure this in the same way you should set up any calculation-based answer. So energy equals power times time. Let's plug in the numbers. So energy is 4,070,000 joules, making sure I've got the right zeros on there. So power is 5,000 watts times time, and time is what we need to find. So we need to do some rearranging here. Get my calculator ready. Now, you might know how to rearrange equations from maths. We need to get time on its own. We need to make time the subject. So I'm going to divide this side by 5,000 watts, and that will eliminate it from this side of the equation, leaving time on its own. But whatever I do to the right side of the equation, I need to do to the left. And so we end up with energy divided by power is equal to time. I'm just going to write this out a little neater on this side so I can show the examiner that I really know what I am doing. 5,000 watts. And that gives me an answer of, just going to make that clear, gives me an answer of 814, which I'm going to write on the timeline. And in physics, we measure time in seconds. So for 4 marks then, we have had to do some rearranging. That's going to count as one of our marks. We've had to give a unit as well, which in this case is seconds, and that would be a 2nd mark, leaving 2 marks for the actual division. All right, so again, I'm just going to dip behind my camera. Okay, so this again is another crossover question between the foundation paper and the higher paper. So you might find this at the top, or one year we did find this at the top of the foundation paper and the lower of the higher paper. I'm just going to move my camera ever so slightly. I'll make that central. I might be able to see the questions a bit better. Yeah, I can. Okay. So here we have a person sliding down a zip wire. Please don't get bogged down in the context of the exam question. You might see this and think, oh my goodness, I know nothing about zip wires and people going down zip wires. I can't do this question. I'm just going to turn over and move on to the next one. Don't worry. The zip wire is just the context. The science behind it is what is important, and you will have been taught the science behind it. So we've got a vertical height. We've got the zip wire, there's the person. Describe how the vertical height of the tower could be measured accurately. In other words, how can we measure how tall something is accurately? Well, what could we do? We could use a tape measure. That's one way we could do it. We could use a, what are those things called? You know, like a laser. My husband does flooring. He lays floors in quite large areas, and he doesn't use a tape measure anymore. He has a laser, and he stands at one end of the room and points it towards the other end of the room, and it measures how long the room is, so you can work out how much floor is needed. So a laser, I think we call it a laser measure. What else could we use? We could use a meter rule. That might be a little tricky though, depending on how high it is. And we've not only got to measure it, but we've got to measure it accurately. So what could we do there? Could we measure it maybe a couple of times just to check that we haven't made a mistake? Now the person using the zip wire has moved through a height of 2 meters. So there's a number, I'm going to underline it. The person has a mass of 45 kilograms. The gravitational field strength is 9.8. Already you might be thinking, this is about gravitational potential energy. And indeed it is. We need to calculate the gravitational potential energy of the person. Again, it doesn't matter that it's a person going down a zip wire. What matters is the numbers. So gravitational potential energy, so energy with a little p, that's energy potential, so that's GPE, equals mass times gravity times height. Let's put in the numbers. Mass, well, we've got to find a number with kilograms after it. 45. Gravitational field strength is 9.8. We need to use 9.8. Sometimes we will be told to use 10. If you're told to use 10, please use 10. If you're not told to use anything, use 9.8. That means for every kilogram, there are 9.8 newtons. And height is 2 meters. For height, we're looking for a number with meters after it. So 2. We don't have to do any conversions here. Everything's in the correct units. There's nothing to square. So we can go ahead and work this out. And it gives us an answer of 880. The unit is already there. So I'm showing you how we should really be setting out our answer to any calculation-based question. Give 3 factors that affected the kinetic energy of the person as she reached the bottom of the zip wire. Right, well, what do we know about kinetic energy? It's equal to 1/2 times mass times velocity squared. Velocity means speed. They are slightly different, speed and velocity. Velocity is speed in a certain direction. It's a vector quantity. Speed doesn't have a direction. It's known as a scalar quantity. But we're asked about kinetic energy and what might affect it. So we can draw on these 2 things. Mass could affect her kinetic energy because mass is in the equation for kinetic energy. Her speed could affect the kinetic energy she has because speed is in the calculation for kinetic energy. Air resistance, you know, she got a massive jacket on, that's going to catch lots of air as she's sliding down the zip wire. Or if she got like a, I don't know, she's just wearing like a vest top or something, and she's not going to experience much air resistance. That will make a difference. And friction as well. There'll be friction between the zip wire and the actual wire itself. So what I've done here is I've made links between what I was asked, which was what can affect the kinetic energy, and the equation. Mass and speed affect the kinetic energy, so therefore they've been my first responses. I know that speed is affected by air resistance, so I've put it there. I also know that it's affected by friction, and so that's where I've got these 2 from as well. So this part is kind of making links between what we know about kinetic energy and being able to apply it to the question. Let's have a look at the mark scheme for this one. So I like to look at the mark schemes for written responses especially. Let me grab my green pen. Okay, so that's the tape measure. Yeah, one person holding it at the top, one person holding it at the bottom. Yeah, because there's ladders there. Yeah, some clues given in the diagram, I suppose. Take repeat readings, so we said that, so we can check our readings. There's the response there. Okay, so again, we can see that although we only needed to make 3 points, there is lots of points we could have made. So lots of opportunity to gain the marks here. So there we could have had height, I suppose. Her mass, mentioned that, speed. Air resistance, you can call air resistance drag as well if you want. I prefer air resistance, but drag's appropriate. Friction. Oh, the gradients are how steep the zip wire is and the length of the zip wire. So there was lots there that we could have dipped into to get our 3 marks. It says there, ignore gravitational field strength, because gravitational field strength isn't going to vary. It's 9.8 newtons per kilogram as long as we are on Earth. If she did another one of these zip wires on the moon, then gravitational field strength would affect things, because it would vary between here and the moon. On the moon, I think it's about 1.6 newtons per kilogram. But it's obviously all taking place on Earth. So gravitational field strength does not vary, and so therefore is not going to be a factor in affecting her kinetic energy. What we're looking for here is things that can change. I'm just saying this again, just for the benefit of people who've joined us since I said and then said again, if you have any questions as we're going through this, please type them in the chat. Please reference the question number, which is in the top right-hand screen. Top right-hand corner of the screen. And also, if you've just joined us, if I'm bobbing around a bit, it's because I'm having camera issues. It's right in the center of my screen, and it's definitely in the way. Okay. Right. This question here is from a foundation paper, and the next question is the same context but from a higher paper. So I wanted to show you the difference between them. So we've got a figure which is showing us a theme park ride called the Aqua Chute. I'm sure we've all been or seen something like this at some point. Riders of the Aqua Chute sit on a sled and move down a slide. There is a layer of water between the sled and the slide. How does the layer of water affect the friction between the sled and the slide? So we've got to tick one box. Please only tick one box. Don't think, well, I'll tick them all and I've got to get the mark. Won't be looked at. If more than one box is ticked, the examiner will ignore it. It'll be marked wrong. Friction is decreased, friction is increased, friction is not affected. Imagine going down this without any water. You probably wouldn't get very far. So the friction is decreased. Makes for a more fun ride, I suppose. Right. The mass of one rider is 62.5 kilograms. Going to underline that. It's a number. It's mass because it's in kilograms. The height of the slide is 16 meters. Gravitational field strength is 9.8. That's the gravitational field strength I need to use because it's been given to me. Don't use 10. Calculate the gravitational potential energy of the rider at the top of the slide. Again, the fact that it's a person on a theme park ride called the Aqua Chute doesn't matter. Basically, we need to put numbers into this calculation to get an answer. So gravitational potential energy, so energy with a little p, equals mass times gravity times height. So I'm setting out my stall to the examiner. Right, I know what I'm doing here. Then I'm going to go and get the numbers I need. Right, 62.5 was the mass. Gravity is 9.8. And how high was it? 16 meters. There's no units to convert. Everything's in the right units. So mass is in kilograms, height is in meters. I can go straight ahead and do that sum, and it gives me 9,800 joules. Unit is already there. 2 marks for doing the sum. At the bottom of the slide, the speed is 12 meters per second. The mass of the rider, still the same, 62.5 kilograms. Calculate the kinetic energy. So kinetic energy, E with a K, equals a half. It's always a half, times mass, times speed, which is V for velocity. squared. Don't forget to square the speed. If you don't know how to use the squared function, times the number by itself. 0.5, I'm going to plug in the numbers. 62.5 times by 12 squared. Then I'm going to do the 12 squared, and then I'm going to write it out again, so I'm keeping myself right step by step. Now I've got everything correct, everything's in the right units, the squaring has been done, and it gives me a number of 4,500 joules. Okay, 2 marks. Putting in our numbers and working out an answer, units are already provided. Okay, part of the same question. The rider reaches the bottom of the slide. The sled decelerates, that means it slows down, and stops. Give 2 factors that will affect how far the sled will move before it stops. Well, I suppose it's going to depend on the speed it was travelling. The faster it goes, the further it's going to travel. I suppose really this is asking us about stopping distances, which is also part of physics. So in other words, how stopping distance is how far we travel while trying to stop. Usually it's used with reference to cars. How far does a car travel whilst it's trying to come to a stop? And the things that affect that are speed. That's why there's speed limits, 30 miles an hour. You know, there's a reason why speed limits are 30 miles an hour. So when you're traveling at 30 miles an hour, you can stop in a relatively short distance. If you increase that to 40 miles an hour, you travel longer while stopping, more chance of an accident and hurting someone. So speed affects stopping distance. We could also have air resistance will affect things. You know, if you're on a ride or a slide and you want to go faster, you make yourself small. That's to reduce air resistance so that you can reach a higher speed. So that will affect how quickly, no it won't, that's not what we're asked about time, we're asked about how far. That will affect the distance we travel while we're stopping. And the friction as well, how much friction there is. So there's minimal friction here because it's a water slide. So you're probably going to travel quite far before you come to a stop. But that would make a difference. If I remember being on wasn't a water slide, but it was like a big tire. You sat in a big tire and you went down a really big dip. And it was really quite scary. I could have flown off the end. But at the end, they changed the surface. The surface becomes really rough to increase the friction between the tyre and the surface so that you're going to slow down as energy is transferred from the kinetic energy store of the tyre to the thermal store in the surroundings due to friction. So you slow down more quickly. So yeah, friction will make a difference as well. Okay, and that's about, we could have had mass as well, and the surface type, which I suppose links to friction. Okay, so this is the same context, but this is from the higher paper. So I wanted to show you the difference between them. So we've got the same aquachute thing, and this time we are told that we have a light gate and a data logger. You may have seen one of those when looking at the acceleration RPA in school, or you might have seen it on a video. We use the light gate and a data logger to determine the speed of each rider and the sled. What 2 measurements do we need to take to determine the speed? Well, for me, I start to think speed is distance divided by time. How far something has travelled and how long it took to travel that distance. Those 2 things divided give us speed. So what 2 measurements here are going to give me distance and time? Gravitational field strength, no. Length of the sled. Right, well, that's going to give me distance. Mass of the rider and sled, that's got nothing to do with speed. Temperature of the surroundings, that's got nothing to do with speed. Time for the sled to pass the light gate. Yes, that's our second one. Even if you didn't know how to work out speed and you didn't know you were looking for distance and time, just, try and use common sense. Determine the speed. Gravitational field strength has got nothing to do with speed. The temperature of the surroundings has nothing to do with speed. I can see why potentially mass you could link, because mass is part of the equation for kinetic energy. So we could have gone with that one. I could see the logic in that. But we're not looking at calculating kinetic energy. We're looking at calculating speed. For speed, we need two pieces of information: distance, that we will get from measuring the length of the sled, and the time, which we will get from the light gate. Right, so you can start to see here the different level of demand in the questions. Right. So the decrease in gravitational potential energy of one rider on the slide was 8.33 kilojoules. Straight away, I'm thinking, that doesn't look like it needs to. It is not in joules, it's in kilojoules. So there's going to be a conversion at some point. 1 kilojoule equals 1,000 joules, just like 1 kilogram equals 1,000 grams. The rider moved a vertical height of 17 meters and gravitational field strength 9.8. We need to calculate the mass. Oh, there's a couple of things going on here. It's not as straightforward as gravitational potential equals mass times gravity times height. We're not working out energy, we're working out mass. So we need to rearrange this. Before we get to that point, let's put in our numbers like we've been doing. So energy, 8.33 kilojoules equals mass, which we need to find, gravitational field strength and height. Right, the first thing I'm going to do is to turn kilojoules into joules. Mass I'm still needing to find. Okay, so I've done my conversion. Just checking I've got that one right. My fingers are cold and it's affecting how I work on my calculator. I didn't think that was right. Missed off a 0. Where's my pen? So if you're not sure how to do the conversion, we need to take our number in kilojoules, which is 8.33, and because there are 1,000 joules in 1 kilojoule, we are converting between kilojoules and joules. Our number is going to get bigger, and therefore we need to times it by 1,000. So there we go, that's correct. Right, so we've done the conversion. Now it's 4 marks, so we've got to work for our marks. We've now got to rearrange this to find mass. So we're going to get mass on its own. So I'm going to divide this side by 9.8 by 17. That gets rid of it. But whatever I do to the right side of the equation, I need to do to the left side. I'm going to work that out separately. Running out of space. So I'm going to work that out separately. It's 166.6. Now I'm going to go ahead and do my final calculation. So you can see I work everything out separately. I don't just plug this into my calculator, 8,330 over 9.8 times 17. I like to do things step by step. So anything in the brackets, I go ahead and work out, breaking it down step by step. Time. Right, and finally, I like this one. At the bottom of the slide, all the riders and their sleds have approximately the same speed. Explain why. And I suppose that's important for safety. We need to know the speed that the riders are, going to end up at. So we know what safety measures to put in place and to prevent accidents. And to explain this, we need to really draw on the link between gravitational potential energy and kinetic energy. So at the top of this ride, the rider and the sled has an energy store which is full of GPE. At the bottom of the slide, that decrease in gravitational potential energy is equal to the increase in kinetic energy. Of course, there will be some loss due to friction and air resistance. So the decrease in potential energy is equal to the increase in kinetic energy. So therefore, mass times gravity times height is equal to 1/2, 0.5, times mass times velocity squared. Well, we can get rid of mass on either side. That's the same on each side, so it cancels out. So therefore, we are left with gravity times height equals 1/2 times velocity squared. Remember, velocity is speed. It's speed in a given direction. Well, gravity and height, they're going to be the same because we're on Earth, so it's always going to have the same number. And the height of the ride is always the same as well, so that's not going to change either. The only thing that could vary here is the speed. But because gravity and height remain the same, any variation is due to our speed, which they are all going to have this approximately the same at the end of this ride. There may be differences, subtle differences due to air resistance and possibly due to friction, but because the sled, is it a sled? Yeah, it's a sled, isn't made out of the same material. And the slide is made out of the same material. Presumably those differences are going to be minimal. But this question really relies on us being able to make this link between the decrease in potential energy and an increase in kinetic energy. And wherever you need to link these two equations together, we do use this assumption. Of course, it's not 100% efficient transfer because energy will be lost through friction and through air resistance, but we're always asked, or usually asked, to ignore losses due to air resistance and due to friction. So if you're doing the higher paper, it'd be really good to focus in on practicing linking these equations together, the equation for GPE and the equation for kinetic energy. Okay, I got rid of that. I'm just going to stop my screen share and I'm just checking in the, let's see, close that. I'm checking in the chat. Okay, I can see there's been no questions. Okay. Well, I hope you found this useful. It has been recorded, so you will get the recording sent so you can watch it later if you need to. Those of you who are signed up for next week, I will look forward to seeing you then. Have a wonderful evening. Take care.